These are not, unlike the stickers, these are not giveaways. I want them back intact. This one is a piece of the Allende meteorite. It's a material out of which the planets formed, or thought to have formed, or out of which the stuff that formed the planets formed, or formed out of the same stuff that formed the planets. It's formed at the same time as the planets. This is just for fun, and it's got a piece of the fusion crust on the outside where it heated up as it passed through the atmosphere. And I've got a piece of one of the Martian meteorites. This is a piece of Sagami. I became convinced that these things really are from Mars. And just briefly, the evidence is these are most of these are young volcanic rocks. And for it to be young volcanic rock, it has to be from a planet big enough to be geologically active within the last billion years. And that really means the Earth, Moon, Mars, or Venus. The oxygen isotopes absolutely rule out the Earth and Moon. And there are several dozen of these Mars meteorites, and they group together compositionally. And a couple of them have a component of gas trapped within them that is identical to the composition of the Martian atmosphere and is thought to have been implanted into the rock by the impact that ejected it to space. So that ties these pretty convincingly to Mars. To me, the fun of this one is to hold in your hand a rock that you know deep in your heart came from Mars. It says something about me, but I think that's just exciting. And when I became convinced that these things are from Mars, I had to have a piece. You can buy them from meteorite dealers. The going rate at the time, yeah, please take it out and touch it. Do not taste it. It's going around and everybody will want to. I'd hate to be at the end of that line. When I bought this, the going rate was $100 a gram to buy this from one of the dealers. And I figured this was much more interesting than what some of the CU students would spend $100. The rate right now it's bounced around. After the whole Allen Hills meteorite discussion that I mentioned last night, the rate was as much as $10,000 a gram. This is 1.5 grams, so I figured a rock, a boat. A rock, a boat. I'm not sure I made the right decision, but I have this cool rock.
You know, the rock is actually a hole in Mars they filmed me at.
I thought that's what a boat was. And this one I just brought down because it's fun as long as I'm passing samples around. Please don't take this one out because it's a very small sample. It's one of the lunar meteorites that based on the composition, pretty convincingly came from the moon. And I think these are just cool to have. But we're not here to talk about that. We're going to talk about the MAVEN mission. And I want to start with a one-chart summary. I'm going to go through the science, the technical implementation, where we are, and tell some, I hope, fun stories. But I want to start with the one-sentence summary. We started developing MAVEN 10 years ago, and I was talking with Janet. It was a conversation between her, me, and Bob Lynn that I count as day one. That was just about 10 years ago. Bob was originally the deputy PI, but passed away last fall. Janet she didn't say this in introducing herself, but she is now the deputy PI. So I'm relying on her to do everything I don't want to do on MAVEN. We are under 3 months to launch. I've got to shift and stop counting in months. We're 12.5 months. The spacecraft is complete. By that I mean everything's done. Right now the solar panels aren't on it, the articulated payload platform isn't on it, but those things go off and on, so I consider it complete. What is exciting to me is that as built, all of the science instruments and the spacecraft have the full capability that we intended when we proposed it, which means we can really carry out the mission that we wanted to carry out when we started this. Environmental testing is complete. We shipped the spacecraft down to Cape Canaveral at the beginning of this month on August 2nd, and we are in the final stages of preparing for launch. The launch period is a 20-day period between November 18 and December 7. But as I was telling some of you, as margin has been released and our mass has not grown, we can actually go about 12, 13 days past December 7th if we have to. We want to have as much opportunity there as possible, because if we miss the launch period, it's 26 months before we get to do it again. If we launch on November 18, we arrive at Mars on September 22 of next year. Our science primary mission is 1 Earth year in duration, and we have fuel, and hopefully we'll get NASA approval to do an extended mission. In the best scenario, we might be able to go for as long as almost a full solar cycle. So I think that would be tremendously exciting. As of today, the technical development is on track. We are on schedule, and we are on budget. That is also very exciting for me to be able to say, that on budget thing especially. So I want to start where I left off last night with what I consider to be the overarching question for Mars. And Leonard, you can see I really do start from the life on Mars perspective. You've heard Mars meets all the environmental requirements for life, and it's not a stupid idea that Mars could have life. It's a legitimate question of did it ever. Once we get to that life question, it also begs the question of how would life have interacted with its planetary environment? What was the nature of the environment? What was the nature of the climate over time? What was the nature of the habitability of Mars by microbes? And how has that habitability changed over time? These aren't the question at the top of the chart, but they're the next level of questions. Given the difficulty of answering the question about life, we want to understand what the answer to that will mean when we get it. And MAVEN is designed to address some of the key questions that don't relate to life directly, but do indirectly. And those are about the climate history, the history of water on the planet. So as you know, I'm going to repeat some things that you've heard through the course of the day so far. The question that we're focused on is, where did the water go? Where did the CO2 go from an earlier thick atmosphere? And we've talked about the evidence for water. Nick Schneider said that correctly that the CO2 in the water can go up or down. We have evidence that it has gone down into the crust. We see deposits of carbon-bearing minerals. This is sliced through the Allen Hills meteorite, and you can see these buds that have been filled with carbonate minerals. And it can go up and be lost to space. And these are measurements from the Mars Express spacecraft showing ions that have left the Mars atmosphere. So we know that escape occurs. We know that formation of carbonates occurs. What we don't know is whether either of these processes was the dominant process in the history of the atmosphere, and which one. What we don't know is the relative importance of these. All the effort over the last, or the bulk of the effort over the last 2 decades has been looking at CO2 in the crust, and we're going to provide the flip side of that, of asking how important, of answering how important has lost to space been in the history of the climate, in the history of volatile. Listening to the discussion this morning, I threw this chart in because it really is the driver behind MAVEN in many ways, using the isotopic evidence that points to escape as having been important to pose the question. Nick talked about the ratio of deuterium to hydrogen. These things can escape thermally. The hydrogen escapes more quickly than the deuterium. What that means is that as gas escapes, the hydrogen escapes more quickly. The stuff that is left behind is enriched in deuterium. So if you measure the ratio of D to H, deuterium to hydrogen, it's going to start out at some initial value, and over time, as gas is lost, it's going to increase. Today, that ratio is about 5 times the terrestrial value. And no matter what you take as the starting point, whether you use terrestrial value or Allende, which is going around, you end up with the conclusion that D to H is significantly enriched on Mars. And that means, since the D and the H come from water, that you've lost a significant fraction of the water, of the hydrogen from the water to space. The models can predict number, but it's of order 3/4 of the water that was on the planet at one time is no longer on the planet. It has been lost to space. We can look at other gases that escape, and you reach the same conclusion. I like looking at the ratio of the isotopes of argon, 38 to 36, because argon doesn't react with anything chemically, and once you put it in the atmosphere, it sits there or can be lost to space. And when you measure it, this measurement is from the Martian meteorites. Mehdi Bennett is going to talk about some of the SAM measurements, but you get a number that is enriched relative to the terrestrial value, relative to meteoritic values, and that requires loss to space to have happened. Across all of the different isotopic systems on Mars, you get a consistent picture of enrichment of the heavier isotope requiring loss to space. This is actually how I got into doing MAVEN, wanting to understand what the effect was on the climate, realizing that it's the escape out the top that may have been the dominant process, and wanting to try to quantify that. Any questions about this before I move on? Because to me, this is so central to understanding MAVEN, it's worth spending a few more minutes on it if there are any questions. Yeah.
So, just to make absolutely sure I get it, the amount lost to space is the amount of that particular isotope?
Yeah, of that gas. So for argon, to get this ratio, this enrichment, it's a slightly model-dependent number. We calculated you would have to have lost between 50 and 90% of the argon that was ever on the planet.
Okay. And that's not necessarily broken down to it's 59% of the argon 38, it's just argon in general.
It's really argon 36 because that's the most abundant argon.
Okay, so it's the one that's on the
Yeah.
right side of the
Yeah.
Okay.
Because in each case, that's the most abundant of the gas. For example, carbon 13 and 12. Carbon 12 is 89 out of 90 of the atoms that you're going to find. So it's really the one that you're talking about.
I'm sorry, I probably said this, but I'm a verbal processor and I was also distracted by the rock. That was really exciting, just like you said. Where it says measured value, that's, I mean, it's called measured value, but that's what we've measured so far, what we expect to find with MAVEN, what we're trying to corroborate.
This is from a paper I wrote 10 years ago. So all of these values are measured in the meteorites that have come from Mars.
Okay.
So it's not a direct measurement of the Martian atmosphere. Mehdi's going to talk about some direct measurements made from the Curiosity rover that really are direct measurements. These are inferred, and they're probably reasonably close.
So what you're going to look for with MAVEN is how it's similar and how it's different. And those are the things you're looking for with MAVEN. All of that, but just maybe it'll be different numbers.
With regard to this, what we want to do is we're not going to measure these numbers any better. I think the Curiosity rover has done the measurements in the bulk atmosphere. What we're going to measure is what's the relative escape rate of D and H? What's the relative escape rate of argon 38 and 36? And that helps us know how to get this number in the right-hand column. Does that help?
You're measuring like the current escape rate?
Yeah.
So,
Let me ask you now to hold the question
Okay, all right.
for about 6 more charts.
sure.
I'm do you know how much of it must have been lost to space? In the third column of the chart there, how do we know what we know already?
When if you suppose you have a box, the atmosphere is a box, and we have some number of each of them, argon 38 and argon 36, and we release them out the top and they're lost to space, and we measure, for example, 238s. One 38 leaves for every 236 that leave. The amount in the box gets smaller. We can write down an equation without too much math that tells us if we know the ratio of the escape rate, what the ratio would be in the stuff left behind as a function of how much has been removed. And that gets us this number. The reason there's a range here is you can also have things like volcanic outgassing that put fresh gas into the atmosphere and partly reset that ratio. Does that help?
Yes.
Let me just follow. What you're going to talk about in 6 slides or so, that is the loss of the past loss. How you got that?
Okay, let me talk about it now
Versus the current
since we have a couple of questions. What we're going to measure is the escape rates today.
That's clear.
And we want to understand not just the rate, but how the processes work that lead to the escape. Because if we understand the processes, we can extrapolate today's rates back to early conditions.
Right, but the early conditions, this is what I want to get to exactly. The atmosphere was different. It was thicker. There was a magnetic field, so it's got to be different. So what I want to know is you're extrapolating the past, the current to the past, but the past is different.
You're good, because that's an incredibly insightful question and a very difficult one to answer. Because what we can measure is what's going on today. And anything about what was happening in the past has to be inferred. And some things we think we can infer better than others. We think that issues like the composition of the atmosphere that has varied through time because we're getting rid of some of it. We know how to deal with that. In part it doesn't make that big of a difference.
Because this is what I didn't understand. I read that blurb on the MAVEN website, and that kind of the press releases, and that's what I really don't understand is about figuring out the past.
What I like about the isotope ratios here is that they're a global indicator of loss to space. It's integrated over the whole planet and integrated over the last 4 billion years. So interpreting these is a little bit less model dependent than trying to extrapolate the processes back in time.
And which of these isotopes, you said it, but I didn't quite catch it. Which are you measuring?
We're going to look at all of them.
Oh, all of them, not
Yeah.
just the first two.
No, but
Deuterium and argon.
I focus on these two because they're easiest to understand. For me, at least.
Are there others too, or just those 5?
These are the key ones. They're the ratios of the atoms that form the climate-relevant gases, like CO2 and water, nitrogen, CO2. Argon isn't climate-relevant, but it is such a good indicator of sputtering loss that Vanna talked about that it's the one I focus in on.
What about anything for like phosphorus?
The amount in the atmosphere is so small that I'm not even sure we could detect it.
I know it's small, that's why I'm asking.
We're,
The limit.
we're focused on the things that are gases in the atmosphere and the loss of gases to space.
You're going to be measuring, because you're dipping in the atmosphere.
Now let me ask you to hold that for a few more
Okay.
seconds. So in this context, we're interested in the history of escape and we have a working hypothesis here that's already been talked about, that early on the magnetic field stood off the solar wind and kept it from hitting the top of the atmosphere and stripping the gas away. When the magnetic field turned off, it allowed the turn on of stripping of the atmosphere. It's shown cartoonish form here, just stripping the atmosphere away, leaving us with the cold, dry planet we see today. What we're really going to do is try to understand each of these processes. We think that these are the important processes based on measurements we've made at Mars, very limited measurements from Mars Express and from other missions, measurements that have been made at Venus, which isn't Mars, but has some similar physical processes, and some analogies with the Earth. We tried to list all of the processes that we thought were important, and we want to measure the things that let us understand those processes. So this diagram shows the energetic stuff from the sun hitting Mars, and that can be the extreme ultraviolet photons, it can be the solar wind, and it can be solar energetic particles, SEPs. Involved in this would be things like coronal mass ejections, flares. All of this stuff can hit Mars, put energy into the upper atmosphere, and strip away gas out the top. And it would strip away gas through these different processes. The ones in blue relate to processes involving neutrals. The ones in red relate to processes involving ions. And I'm not going to go through these. I just wanted to show you that we've worked through a lot of the processes. What we hope is that we've designed a robust enough payload that not only will we see and understand these processes when they're occurring, but when we get there and we discover that we didn't have these at all right, that completely different processes are taking place, that we'll be able to understand those as well. So the highest level of objectives are first to determine the present state of the upper atmosphere, composition and structure, and understand the processes that control it. I thought that was a different bullet. And the second bullet, that's what happens when you juggling charts at the last second. The second bullet right here is to understand, measure the escape rates today at the present epoch, and understand the processes that control them. And then the third is to take measurements that will allow us to extrapolate these processes back in time, to understand what the history of escape to space has been. To do that, we've designed a payload that measures those things. It measures the energy input, it measures the response of the upper atmosphere, and it measures the escape rate. So we've got the neutral gas and ion mass spectrometer. Betty will talk a little bit about that, being led by Paul Mahaffey at Goddard. We've got the imaging ultraviolet spectrometer that Nick is leading. To my mind, these are key instruments because the NGIMS instrument, the mass spectrometer, tells us in great detail the composition of the upper atmosphere and ionosphere at the location of the spacecraft. So we pass through the upper atmosphere and measure it directly, and then we can use the ultraviolet spectrometer, the imaging ultraviolet spectrometer, to extrapolate to global characteristics. We get detailed point measurements, and we get global measurements to compare it to. To me, that's an incredibly powerful handle on understanding the structure, composition, and escape. So I see those as key instruments. Now I see these others as key instruments as well, because we're going to measure the solar energetic particles. That can be a key driver of escape. We're going to measure the solar wind electron properties and the solar wind ion properties as the solar wind hits the planet. That can be an incredible driver of escape. And we're going to measure the escaping ions, which is, after all, what we're trying to understand, the escape. So we're going to measure that directly. We're going to measure the magnetic field to try to understand the environment and the processes where this is happening. And then this bizarre thing called the Langmuir probe, that lets us measure the characteristics of the electrons in the ionosphere. As a part of this, we also have a detector that looks at the sun and measures the extreme ultraviolet photons coming from the sun directly. So we're measuring every aspect of this cartoon that I showed you back here that's measurable, and that lets us understand the entire system. So even though I said these two are the most important, these 6 are the most important. They're really all important. We wanted to measure all aspects of the system. I'm not going to talk about the instruments in any more detail unless you have questions, because we would be here all day.
Can you just tell us about how these instruments, what we don't know, this is all relatively new information, right? What do we learn on the past probes in these areas? That's what.
Okay. Every one of these instruments has flown in space or something very close to it. Not all of them have flown at Mars. Not all of them have flown at the same time. So at Mars, see if I can do this on the fly, we have flown a magnetometer. So we know the magnetic field of the planet, but this one is designed to measure the magnetic field relative to the ions and electrons, because the magnetic field controls them. Aspects of the electron and ion analyzer have flown on the Mars Express mission. I mean, not this hardware, but things that measure similar things. But again, we're flying these and measuring the magnetic field at the same time, and measuring the response of the upper atmosphere at the same time. So although some of this has flown on Mars Express, which is orbiting still, not all of it has flown at the same time, and it's that simultaneity of measurements that is really the key to the MAVEN analysis.
Thank you.
So you have to put these instruments on something, and we have the spacecraft. Dick brought his model of the spacecraft, and you can come and take a look at it. I just have a cartoon version here, but let me walk through it briefly. We have some instruments, as you inferred from what I said, that want to look at the sun or the solar wind, and some that want to look at the planet. So you have to have something that bends and twists. And what we decided was we would have the body of the spacecraft point at the sun, and we would have an articulated payload platform down at the bottom that has 2 gimbals so it can orient in any direction. So the instruments that want to point at the sun are mounted on the body of the spacecraft. Those that want to point at the planet, which is 3 of them, the imaging ultraviolet spectrometer, the static instrument, and the NGIMS instrument, those that want to point at the planet are mounted on the APP. To give you a sense of scale, this is the high gain antenna. It's 2 meters across. So from the floor up to there. You can see that the bus itself is a little bit more than that, square, and not quite as deep as it is square. The solar arrays, Nick, I'm glad you brought this model.
Careful, the APP falls off, which I hope doesn't happen in flight.
It will only if you annoy me. Pull tag that says eject.
I'm taking many with me.
You can see that the solar panels have this bend in the middle. And the reason is so that when the spacecraft passes through the upper atmosphere, it will do so in this direction, and it makes it a little more aerodynamically stable. Several of the instruments are mounted in the corners on the bus around the high gain antenna. The magnetometers are out at the end of the solar panels. They want to get as far away from the spacecraft as possible, so they're not measuring the magnetic field of the spacecraft. The solar wind electron analyzer is out at the end of this boom that sticks off toward the back. You can see it on the model sticking off back and down. Also to get it away from the spacecraft, because electrons are very susceptible to any charging that the spacecraft has. That'll perturb the energy, the velocity, the direction of the electrons, and then you won't be measuring what you want to be measuring. And then the Langmuir probe sticks off at the end of these two 7-meter booms that stick out like little rabbit ears. Yeah?
Sorry, silly question. Why would these spacecraft have magnetic field?
Everything has a magnetic field.
Okay.
Some of the instruments, the mass spectrometer is a good example. It works by changing the direction of ions with a magnetic field. So it has magnets
Okay.
in them.
So there would be magnets on
Yeah.
board that could.
And anytime you run a current in a loop, like in a circle, it generates a magnetic field. We have worked really hard to minimize the magnetic fields on the spacecraft so that it doesn't affect the magnetic measurements. As an example, think about it. You've got these solar cells, and they're all lined up on wires. So each one is creating a current loop. So we get around that by, we have a current loop going this direction, we put a wire on the back of it that runs in the opposite direction. So it cancels it out. We have worked hard with a magnetics cleanliness program to minimize the field. And as of today, it looks like we're within spec, so we've succeeded. The Langmuir probe measures the electrons, and again, it wants to be as far away from the spacecraft as possible, so it's out at the end of those booms. That's all I'm going to say about the spacecraft, but I do have some pictures coming up.
Okay, before you go on, can
Yeah.
you just talk about whether you were going to have to rotate this spacecraft for the different measurements?
When we set out, the intent was to minimize that, but it turns out that there are times we have to do that. The goal is to make as many measurements as possible. Trying not to drop the APP off there.
You also just yank it off and not worry about
That would be wrong. So if that model of Mars is the sun, I hate to do that. We want to have the spacecraft pointed at the sun as much as possible. We want the sunlight on the solar panels. But there are times to get the measurements, we have to rotate it about 90 degrees. There are also times when we want to turn it so that it is traveling butt first in the direction of the flow. We've worked this all out. We have a plan of what we're going to do every day of the mission, subject to change, but we have a plan at least of what it's going to do. We can't make every measurement we want to make every day, keeping the spacecraft in one orientation. We actually have about 10 different ways we're going to operate the spacecraft on different orbits, depending on where the sun is, what part of the orbit we're in, and let me come back to that in a minute. To give you a sense of scale, I've tried my best here. It's the end-to-end, it's the same length as a school bus. I did put this picture together when I was going to visit a school. 37 feet, pardon English units. It's the same weight, fully loaded with fuel as a GMC Yukon. For MAVEN, the spacecraft is about 810 kilograms. The fuel is 1,600 kilograms, so it's fully loaded. For the GMC Yukon, it's with a full fuel tank, 4 adults, and some camping gear thrown in the back to get up to the same weight, same mass.
What was the weight of the mass of
The
the fuel?
1,600. And you're going to see a little bit of inconsistency here, and let me explain it, because somebody will ask. I listed here the wet mass, which is at launch fully fueled, as 2550. But that's our, what we call our not to exceed mass. We can't go above that without getting in trouble with the launch vehicle. Our actual mass, as weighed, is going to be about 90 kilograms under that. And that's really good news because it means we have extra capability, less fuel to get into orbit, more fuel in orbit, longer lifetime. Let me describe the mission architecture. I've already said we have a 20-day launch period coming up in 12.5 weeks. We launch on an Atlas V in the 401 configuration. That means it's the 4-meter fairing, 0 strap-on solids, 1 booster on the Centaur upper stage, one rocket motor. There is one more Atlas launch before ours. It's coming up on September 18th. It's something called AEHF. I have no idea anymore what that is. And I am worried sick over that because if it blows up, they're not going to launch us without understanding what happened. I know that those people are worried about it blowing up for a different reason. If we miss this launch period, then it's 26 months before they line up again. When we launch, we don't go into orbit around the Earth. We go straight on a trajectory to Mars. We do that with it's about a 4-meter burn of the main booster. And then we do 2 burns of the upper stage separated by ½ an hour. They put us on into an orbit around the sun. When we get out to the farthest distance from the sun, Mars is right there. That's the key aspect of the timing. We have 5 trajectory change maneuvers scheduled en route. If we don't need them, we don't need them. The first one we will need because we target to miss Mars by a whole lot. And that's for 2 reasons. One, because we don't want the booster to hit Mars. It's a planetary protection requirement. And the second is we want to do our first trajectory change maneuver, TCM, as a dress rehearsal for the orbit insertion burn. So it runs 2 weeks after launch, exactly how everything will run for orbit insertion, just a shorter burn. And that puts us on target to have the right approach to Mars. When we get to Mars, we fire our rockets to go into orbit, and this dotted line shows what happens if we screw it up, dashed line if we do it right. It's a 38-minute burn, and what is interesting is the burn was designed so that even if the computer that controls it has failure during the burn, it can recover. It takes a maximum of 13.5 minutes to go, holy crap, the computer failed, swap sides, reboot, reacquire the sun, reorient the spacecraft, figure out where I was in the burn, and start up again. And we would still get into orbit no matter when during the burn that happened.
That's all autonomous.
It's all autonomous because we are about 16 or 17-minute one-way light time at the time of orbit insertion. This is one of the things that Lockheed, as the spacecraft provider, has done that is really impressive in terms of designing a system that is resilient against failure. I should tell you, this picture is not to scale. We really aren't quite that big relative to the planet.
So Mars is 1 school bus in diameter?
Yes, it's much smaller than we've led you to believe.
I always knew it was smaller than Earth.
When we're going to land astronauts, it's going to be really tough. All of a sudden, the footprint is going to be the dominant geologic feature. This picture on the lower right is to scale, and it shows the size of our orbit relative to the planet. At the lowest point in the orbit, we're nominally 150 kilometers above the planet. At the highest point, we're about 6,000 kilometers above the planet. The orbit is elliptical, so that every orbit we pass through the very tenuous part of the upper atmosphere. So it lets us sample it directly at the location of the spacecraft, as well as do the remote sensing global imaging from the IUVS. Carolyn, you look puzzled?
I was just wondering what the period was.
4.5 hours. the period and the inclination, I'll come to that in a second, why we picked them. This shows the orbit, again to scale, at one particular moment, and these green things represent the boundaries created by the solar wind interaction with the planet. So it shows you that at different places in the orbit, we want to measure different things. So at the lower part of the orbit, we're passing through the thickest, densest part of the upper atmosphere. It's still really tenuous, so it's not a hazard, but we're making the most detailed measurements of the region from which escape occurs. Nick talked about, or Janet talked about the exobase, the altitude where escape occurs. Every orbit during this part of the orbit, we pass through that region where escape occurs and get above it and below it. So it gives us a really good understanding of what's happening there. At the top of the orbit, at apoapsis, the IEVS instrument is doing global imaging of the part of the disk that it can see. And on the sides of the orbit, the IEVS is measuring the hydrogen column to get hydrogen and deuterium escape, and the static instrument is measuring ion escape. So we have 4 segments in the orbit. During each one, we do something different, and it's all autonomous. And it's all planned out in advance. This chart just shows the part of what I said, where as a function of time, the altitude drops as we're coming toward periapsis, and then goes back up. Every orbit we pass through this region where escape is driven from. And then 5 times during the mission, we drop the periapsis from 150 kilometers to about 125 kilometers. We call these our deep dip campaigns. It's to get the entire column of the upper atmosphere. This takes us all the way down to the region of the atmosphere that is well mixed. It takes us to the homopause, where it stops being homogeneous. And that lets us get the entire column. We don't do this every orbit, because when we drop down below 150, if we leave the high voltage on, you can get arcing, sparking across some of the components. That would destroy the instruments. Plus, if we go down that deep, we have enough drag that it would be like aerobraking. We would have to keep adjusting our orbit. But we do that 5 times in order to characterize that part of the atmosphere.
And these 5 times are at different positions over Mars?
Yes, and I'll show you that in just a moment. This picture on the left is the same thing as I showed you 2 charts ago, except that you can see that the orbit doesn't stay in one place. It precesses so that we cover all the different regions. And it precesses for 2 reasons. Well, yeah, for 2 reasons. One is that Mars, unlike this globe, isn't a perfect sphere. And that means that the gravitational field of which isn't symmetric, perturbs the orbit, and that causes it to precess. If Carolyn, if your head is the sun and my head is Mars, mine isn't that big usually, but and this is the plane of the orbit, that causes it to rotate along that line, and it lets us get different local times as it goes all the way around. The second reason is that in addition to precessing in this direction, it precesses in this direction. And the latitude at which periapsis occurs changes. So again, if your head is the sun, my head is Mars, my left finger is periapsis, my right finger is apoapsis.
Hold that picture, hold that photo. I got it already.
Anybody shoots this, I confiscate the camera. I've done this enough times and managed to keep it off of YouTube. I don't want to go on there.
That should be a DUI test.
So this is periapsis, this is apoapsis. It precesses in local time and latitude. So it does this. Again, Carolyn's head is the sun.
Cue the music.
You try doing this. And as it does so, it gives us this complicated pattern, but it allows us sometimes to get upstream to measure the solar wind before it gets to Mars, sometimes to get down in the wake, where we're in the shadow that Mars creates from the solar wind behind the planet, and other times we cross over all of these regions. And that lets us characterize near Mars space very effectively. We picked the 4.5-hour period and the inclination, which is 75 degrees, to give us the best coverage over all of these regions over the course of the mission. And in simpler form, this shows that. It shows the latitude and longitude relative to the sun on the planet of the periapsis location. So we start with periapsis at high northern latitudes. We swing around in local time and drop down in latitude. Over the course of the mission, we go around the planet twice in local time, and we cover all the different latitudes. The 5 deep dip campaigns, getting to your question, are where these stars are. We picked one to be, this is the subsolar point right here. So one is at midnight at modest latitudes, intermediate latitudes. One is at, Joe, is this dawn or dusk? Can you remember?
Dusk.
Dusk, thank you. One at dusk, right when the sun is setting. One as close as we can get to the subsolar point. And you'd say, why can't we get it right there? The reason is that if periapsis is at the subsolar point, apoapsis, where we're farthest from the planet, is in the shadow. And it's a longer shadow. And we don't have enough power to do that. So we get as close as we can to that point. One at the dawn terminator and one at high southern latitude. This is our best guess ahead of time as to where we would get the most value in measurements. Yeah.
What are the guide stars, just for gee whiz, what stars are you using? These are marking the guide stars, right?
No, I just marked with a star to draw your eye to where these are.
Okay, I know the star. I was thinking the guide stars were the...
Because originally it was coated with this light blue, and even I couldn't find that, so I put little stars there so you could see where they were.
Okay, I just hear stars.
Sorry.
So if you get an extended campaign, which I'm fairly certain you will get, you'll get more, and you're going to try to space it out.
And
Fill in the
during,
gaps.
during an extended mission, periapsis is continuing north, and on this graph it actually turns around like this and then goes out the top again. So it goes back the other way because periapsis will have processed around to the other side of the planet. We designed this for a 1-year mission, which means we picked the inclination and orbital period to give us the best coverage over 1 year, and that's this. Ideally, we'd have filled in this graph entirely, but this is what we can get. We didn't worry about what we would get in year 2 or beyond because we're going to get what we get. We wanted to maximize the value of that first year.
But this mission will continue, right?
I hope so.
Assuming you get the funding.
There's
assuming you get into orbit, there's no reason why this is not going to continue for 10 years or more, because you have the fuel.
Let me give you about 3 answers to that. First, we designed this in a way that we can address our key science objectives to the greatest extent in year 1. That is, we're going to see the most variability of the sun and the most solar storms in that first year. And that will give us a really strong handle on the questions I posed. That's the first point. Second point, that doesn't mean we don't get real value out of continuing. In an extended mission, we have the ability to go through the second half of a Mars year to look for year-to-year variability because some of the atmospheric compositional drivers vary throughout the year, and possibly to last through most of the solar cycle and see the effects of the solar cycle variability. So there's high scientific value of doing an extended mission. Third point is we carry on the spacecraft an Electra relay. This is what MRO and Odyssey and Mars Express all carry to relay data from the ground to Earth, so that the rovers didn't have to carry as heavy communication equipment. NASA wants us to survive because MRO and Odyssey are both getting pretty long in the tooth, and they need to replenish the relay capability. When you look at the 2020 mission, that's a launch year. It gets there in 2021 and then has probably a two Earth year primary mission. You're going out to 2023. MRO and Odyssey are going to be ancient by then if they're still alive. They will have long exceeded their factory warranty, and I would be surprised if either one survived. They desperately need us to survive that long as a relay in order to send data back from 2020.
Yeah, that's exactly what I'm asking.
Yeah. In terms of fuel, if things go well, we should have enough fuel to last a decade. There are things we can do to sacrifice some science in our second year that would let us last a lot longer. I don't know to what extent we will have that option, or will be directed by NASA to maximize longevity. I also worry because 10 years out to 2023 will exceed our factory warranty. And even if fuel survives, we weren't designed for that long a lifetime. The components do have limited lifetime. We designed to our primary mission, which is 10 months to get there, 5.5 weeks transition phase to get ready to do science, 1 Earth year primary mission. We're using a lot of components that have heritage that we didn't degrade, so a lot of it has 5-year lifetime, but some of it doesn't. I can't guarantee how long we're going to survive, assuming we get into orbit safely.
The instruments, they don't have any consumables on them that would limit their lifetime.
Consumables, no, but some of them do have limited lifetimes. In terms of how often they can do things, the Langmuir probe has those 7-meter booms. Those are going to degrade sitting out there in the oxygen environment, even at that very tenuous altitude. And those are probably not going to survive 10 years. I'd be surprised if they did. Again, we designed everything for that 1-year lifetime primary mission, and everything beyond that is icing on the cake. Janet already showed this, but I wanted to show you where in the solar cycle we'll be. You are here today, more or less. We're going to be at an ideal place for making our measurements during a declining phase of the solar cycle, which is when you get the most and the most intense solar storms. I threw this in here because I wanted to emphasize, getting back to your question of how we extrapolate backward in time. We're doing it with 3 different approaches. One, I mentioned the isotope ratios, which is sort of like instant extrapolation. The second is we're going to use physical models of the processes that we will now understand in order to extrapolate those processes back in time and see what happens. And the third is we'll measure variability in the solar input directly and be able to just do an instant extrapolation that way. I wanted to show you a few pictures as well. Actually, I forgot I had this one in. We're doing the mission operations at Lockheed Martin. We're doing the science operations, controlling the instruments at LASP in our other building that you'll see later this afternoon. But I wanted to show you some pictures. Since we have been doing this for 10 years, this goes back to writing the original proposal. The original proposal that we submitted was about this thick, My estimate is it cost somebody in terms of time and effort about $2 or $3 million to produce. We got selected to do what's called a phase A study, to do it in more depth. And you can see the product that came out of that. It was a concept study report that was this thick, and it was so much fun they had us do it twice. We got selected. We had, as part of the selection, we had to do a site visit where we got grilled for a day by a review panel. This was preparing for a site visit. This is sitting in the breakfast room at one of the hotels down near Lockheed, an hour south of here. And a picture taken at site visits surreptitiously because they're not allowed, you're not allowed to take any pictures. Nick, for your benefit, this is George Pace, who was on the site visit. He was also the chair of our standing review board, which just 2 weeks ago completed its last review of MAVEN after all these years. We also had to go and do a presentation to the selecting official. I was invited to bring 4 of my best friends, and we had 40 minutes to make the case. So these are the 5 of us, me in the middle, Ed Sedeby, who at that time was the program manager at Lockheed, responsible for the spacecraft, Bob Lynn, who was the deputy PI, and at either end, I've got Dave Mitchell from the science team, and Dave Mitchell, who's the project manager. See, it's all about redundancy. We have 2 Dave Mitchells, we have 2 Mike McGraths on the team, one at LASP, one at Goddard. We used to have an incredible number of Tims. Tim Preiser, Tim Holbrook, Tim Gasparini, Tim Bowser, Tim Trenkel. And with all those Tims, then I discovered when you have a meeting to talk about details, they call it a technical interchange meeting. Now we just have Bobs all over the place. I mentioned reviews. This is one of the reviews in front of our standing review board. We added it up and got 220 formal reviews over the lifetime of the project up until launch. So this includes the dozen or so that are still to come. What I like to think is they only hold reviews on days that have the word day in the name. See, I think that's funny. Nobody has ever laughed at that. And you'll notice every single person here is sitting working on their laptop. Spacecraft assembly, what they call ATLO, Assembly, Test, and Launch Ops, started in August of last year. And this was very early with the core structure. The fuel tank is in the central cylinder here, and all these bays around it will hold the electronics equipment. This is the core structure being lowered over the fuel tank. The fuel tank has never been seen again. This is late in ATLO now that all the electronics have been inserted. 2 things to note. First, it's an open bay that will be closed with the multi-layer insulation that will keep it warm in flight. But it's an open bay to allow easy access. But the interesting thing is it's not completely filled up with stuff. Because of some bizarre aspects of this APP, the Articulated Payload Platform, and booms that swing out, they needed to have them far enough out that they could keep the center of mass controlled. So as a result, we have a structure with a lot of empty space. You can see here the 4 reaction wheels, each one of which controls about a different axis, and there are 4 so that we have a spare. Once it was completed, that picture was very late in assembly when almost everything was on it. Once everything was on the spacecraft, it goes through environmental testing. On the left here, it's in acoustics, which is where they subject it to the sound it's going to hear on the pad at launch. It's 145 decibels for comparison. The human pain threshold of 125 and 145, I think that's called turn you into jelly, which is why the Atlas V, as currently configured, does not ever have people on top of it. On the right is on the shaker table. They vibrate it because it also vibrates on launch. And it surprised me. I was there watching the first vibe test, and the amplitude it moves from one end to the other. You can see it by eyeball. You can't see it moving, but as it's vibrating, you can see the ends of the motion. It moves back and forth this amount 5 times a second, and then 10 times a second. Imagine, again, being an astronaut on top of that. Again, jelly. They do this because they don't want the spacecraft to see anything for the first time in space, in flight. It has to experience everything ahead of time so you know it can survive. This is the spacecraft just before we shipped it down to the Cape, complete, ready to go, on display for some of the local press. We shipped it on August 2nd, just at the beginning of this month, and this is in a box on a truck pulling out of the garage at Lockheed Martin. And the way I think of it, you know, if you're taking your family on a vacation, the trip really starts when you pull out of the garage at home. So that's really the start of the trip to Mars. It just takes a circuitous route. Like many of us, it goes to the airport first. It went to Buckley Air Force Base and was put into the back end of a C-17. The C-17 flew to Kennedy Space Center and landed in the shuttle landing strip. This picture was taken by our project manager who was there to greet it. You can see me inside the plane. I got to ride with it. The whole cool thing of doing a mission is you get to ride on the C-17. And then loaded into the Payload Hazardous Servicing Facility at KSC. It's hazardous because that's where they're going to fuel it. And the rocket is done. We have the Atlas first stage, the Centaur second stage, and this picture was a week ago. They were taking it by truck. It was built in Decatur, Alabama. It goes by truck to the waterfront where it's loaded onto a barge. The barge will arrive at Kennedy on tomorrow, and it will be unloaded Monday. So the rocket is there, and to me, this is one of the most exciting pictures. It's the fairing that will surround the spacecraft on the rocket with the MAVEN logo on it.
Yeah, there's going to be a media day down at KSC for the arrival of the Atlas.
Is there?
Yeah, I just got the notice last night.
Okay. I'm not surprised. I didn't know that.
Yeah, they don't usually do it, but they did it in this case.
And to me, where I stand, it seems there's so much interest in this because it's a Mars mission. And every aspect gets attention, gets media attention. So it's down at the Cape. This is everything at high level, everything that's going to go through between now and launch. First was inspect it, clean it. Some of the equipment had been removed for shipping, and that had to be reinstalled. Some of the components, like a couple of the Berkeley instruments, have gone back there for recalibration and for some minor rework. Those are reinstalled, and what they call regression testing. You put it through enough testing after you've reinstalled to make sure you know it works. That's completed. Next thing will be to redo system verification test where we run it through its paces for each phase of the mission, where it's actually going to think it's on orbit doing science measurements to make sure that there are no problems or issues. Then you're going to see we get into things connected to launch. We install the pyros, we do the final spin balance, load the fuel, made it to the structure that will support it on the rocket, put it into the fairing, take it out to the VIF, the Vertical Integration Facility, where it's mated with the Atlas booster and the Centaur upper stage. The day before launch, it rolls out to the pad on launch day. They fuel the rocket on the pad. It takes about 2 hours to put in the cryogenic fuel. And then we do the final countdown and launch. And it's easy to focus on launch. It's a really big activity, and it's our single greatest potential for failure because of the number of rockets that don't work. But I just put this in here to remind myself, as much as you guys, that even though launch is a major milestone, it's not the end of it. It's really just another milestone because we have to get to Mars, get into orbit, and start taking data, which is the end goal, to get the science out of it that we're trying to get.
The Atlas so far is 100% reliable. Yeah.
No. The Atlas
The
5.
Atlas 5.
The Atlas 5, not from where I sit, it's had, I think we're up to 39 launches. They count all of them as successes. One of them had an underburn on the upper stage that put the spacecraft into a different orbit. It didn't bother them. If we have an underburn on the upper stage, we're done. So I consider it 38 out of 39. Typical. See, Leonard, these are the things I pay attention to.
That sounds great.
For the last year, I've been watching every Atlas 5 launch going, please don't blow up, please don't blow up. And we have one more.
Yeah.
Historically, they have a 1 in 20, 1 in 30 failure rate, which is really good odds. But tell that to my friend who is the PI on the orbiting carbon observatory. That's the one where the clamshell fairing didn't separate. He was in the control room watching it go up and watching it go down into the ocean after he invested 10 years in developing that.
That was the Taurus one.
Yeah.
Yeah. They did it twice, actually. Two, they were.
Yeah, we had an instrument on the other one, on Glory.
Did you?
Yeah, last year. And as one of our colleagues here says, this business is not for the faint of heart. And the way I look at it, I quote the line from the Godfather movie, this is the business we've chosen. I'm not going to make you guys an offer you can't refuse. My last chart, bottom line, we're on track, on schedule, on budget, 12 and a half weeks and counting to launch. And everybody involved in the project knows that there is ample opportunity to royally screw it up in those 12 and a half weeks. We could do things that because of the short fuse now, we cannot recover from. So we can't get complacent. It requires even more attention now to doing it right than it has for the last 10 years. So stay tuned. I hope we will see you at the launch. I hope we will see you in a year plus when we're starting to talk about the science results. That's what's really going to be exciting. Thank you.
Let's do questions for 5 minutes and then we're going to turn it over to
You know, you talked about being on schedule and on budget. That's not always the case for a lot of missions like this. What do you credit for that performance?
Clean living. Let me try to give you a serious answer because we've had a lot of discussions of how we've managed to go so smoothly. People who have worked a lot of projects have said this is the smoothest development they've ever seen. I think part of it is no requirements creep. We designed a mission up front and we stuck with it. We didn't try to enhance the science. We didn't try to enhance the engineering. Part of it is no new technology development. If you look at MSL, it was technology development that killed them. If you look at James Webb, that's what's killing them. We have very minimal technology development. Those are absolutely key things. We have first-rate people at all of our institutions who have been through this many times, in many cases with identical or almost identical instruments, hardware on the spacecraft, etc. And having been through it with similar equipment really gives you a leg up to do it again, even though it's a mission that hasn't been done before. These are the things that I would list at the start of my list, but I could also go down to about 24 different reasons, including just, let me mention one more. Each mission has to have a NASA Center partner to do the management, or an equivalent, like APL or Southwest Research Institute. We're doing this with Goddard. Goddard has a long history of excellent service on spacecraft missions. This is their first Mars mission, arguably their first planetary mission, and for institutional reasons, they want to do it right. They've given us the A team in the project office. Project manager, his whole staff are outstanding people, and that makes a big difference. It also makes a big difference that they haven't yanked them away to work other projects that are having problems. We've gotten the 18 and we've kept them. And it's like that at every institution. We have outstanding people working this mission. And that really helps us stay on track. Now, these are the things that I point to, but we haven't done a controlled scientific study. So they're the things that I key on, but it could just be dumb luck too. Luck of the draw. I don't know how to figure that out.
Are there any plans for MAVEN to observe on the A1 sighting springs if it gets there in time? Or is it not?
I knew somebody was going to ask about Siding Springs. We get to Mars 3 or 4 weeks before Siding Springs gets to Mars. It is going to pass about 120,000 kilometers away from the planet, which means about 120,000 kilometers away from us. It's in an inclined retrograde orbit, so the relative velocity is about 56 kilometers per second. We're worried about dust grains from the comet that will hit us and do damage. We think we've done an analysis that suggests that there's minimal risk, that it's well bounded by our environmental requirements that we set out at the beginning of the mission. But my first priority is health and safety of the spacecraft and instruments. My second priority is that's in the middle of what we're calling the transition phase, where we're commissioning the spacecraft, deploying the booms, testing everything. So my second priority is Mars, and my third priority may be observations of the comet. So stay tuned. We'll see where we get.